I want just one last fact from algebraic geometry. Remember, I'm actually trying to move to Lie algebras, so we're going to start doing linear algebra. So things are going to get easier quite soon. But just to make this picture make sense, we need to say one last little piece. So here's the last fact I'm going to appeal to. I'm not going to prove this. Let X be an irreducible affine variety, then the dimension of the tangent space at some point is greater than or equal to the dimension of the variety X. So this is for all points little x in big X. And moreover, equality holds for all x in some dense open subset of the variety. So these x's where the tangent space has kind of the right dimension, where the dimension of the tangent space is equal to the dimension of the variety, these are called the simple points of X. And if it happens that all points are simple, then X is called smooth. It's pretty easy to come up with examples. I don't know, the simplest example I can think of is t1 squared minus t2 cubed, the vanishing set of that polynomial in affine 2 space. So this is some sort of cusp. And at the origin, there's a singular point. So at all the points of this curve, this x, it's one-dimensional. At all the points except for the origin, the tangent space is just one-dimensional as you expect. But at the origin, the tangent space becomes two-dimensional. So the dimension of the tangent space blows up a little bit at the origin. So this is a singular point of this affine variety. But smooth is all we care about because algebraic groups are smooth. For algebraic groups are very homogeneous. Left translation by some element in the group, that's a homeomorphism. And so with these homeomorphisms, you can take any point to any other. So from the algebraic geometry point of view, algebraic groups, they kind of look the same everywhere. Every point in an algebraic group is a translation of the identity. And so since by the theorem, simple points are dense, so a generic point is a simple point, but in an algebraic group, every point is generic because of this homogeneity. That means that in an algebraic group, every point is a simple point, so algebraic groups are smooth. So for an algebraic group G, the tangent space dimension of the tangent space to G at any point, well, we may as well just take the identity point now, right? Because every point looks the same. The dimension of the tangent space at the identity is equal to the dimension of the group. Oh, I didn't put my algebraic group was connected, so I should put connected component in there. I don't want to ever be taking dimension of some variety that isn't irreducible. Great. Okay, so that's kind of the last little piece of algebraic geometry, and now we're heading very quickly to Lie algebras. So the main goal today is I want to explain how to make this tangent space to an algebraic group at the identity. I want to explain how to make that into a Lie algebra in a natural way. So to do that, we need one more definition. Let G be an algebraic group So I'm going to define this thing, I'm going to call it L of G. So this is just a vector space to start with. It's the vector space of all derivations from the coordinate algebra of G to the coordinate algebra of G with this property. Lambda G composed with D is D composed with lambda G for all elements little g in the group. Okay, I haven't told you what lambda G is, so this doesn't make sense yet. But let's name this thing. This thing is going to be called the space of left invariant derivations. So what is lambda G here? Well, lambda G is going to be an automorphism from the coordinate algebra to the coordinate algebra, and it's called left translation by some element little g in the group. Actually, we'd already seen rho g, hadn't we? We'd already seen right translation. I used that when I was proving that every algebraic group was linear. And rho g, so this was a left action of the group on its coordinate algebra, a linear left action, and the way rho g what rho g did to a function f was it was a new function whose value at some other point h was f of h times on the right by g. That was our right translation action. But in a very similar way, you can have a left translation action. So the formula for that, lambda gf, that function is defined on h to be f of, so now I want to multiply on the left by g, because I want it to overall define a left action of the group on the coordinate algebra, I need to sneak in an inverse there. So it's g inverse h to be a left action. Okay, so that's what this lambda g means, and then L of g, it's all the derivations which commute with all these left translations. So we know already that derivations from an algebra to an algebra always form a Lie subalgebra of the Lie algebra of all linear maps from K of G to K of G, right? So this is our general linear Lie algebra. So that's all linear maps from that vector space to itself viewed as a Lie algebra via the commutator. And we'd already observed when I first talked about derivations that derivations of an algebra always gave you a Lie subalgebra of the general linear Lie algebra. In other words, the commutator of two derivations is again a derivation. In fact, this L of G is a Lie subalgebra of that Lie algebra of all derivations. This is pretty obvious. I mean, all you have to do is see that if you take two left invariant derivations, d1 and d2, and compose on the left with some lambda g, so what's that? That's lambda g composed with the commutator, that's just this expanded. And I think I'm not going to write out all the lambda g commutes with d1 and d2, so you can pull the lambda g to the right here, and you end up with the commutator composed with lambda g. So that's all you have to check, right? Is that if you take the commutator of two left invariant derivations, that commutator is again left invariant. So L of G is a Lie algebra in a very easy way. Great. So why is that relevant? Well, we're going to prove the main lemma today, which says that there's a linear isomorphism from the space L of G, this thing which is naturally a Lie algebra, to the tangent space. And that isomorphism sends a left invariant derivation D to D bar. We already had D bar before. Remember D bar, that was just composing with evaluation at the identity. So that was that natural way to take a derivation and turn it into a point derivation, composing with that evaluation at the point E that we're looking at here. Okay, so that easy map from L of G to the tangent space, D goes to D bar, it's actually a linear isomorphism of vector spaces. So this is why I care about L of G, which is a Lie algebra in a very easy way. Then once we prove the lemma, what we're going to do is we're going to take this easy Lie bracket on L of G and we're just going to transport it to our tangent space, that vector space which we understand well as a vector space. And that will give us the desired Lie algebra structure on the tangent space. But so we've got to go and prove this lemma. So let me maybe add a little bit more to the statement of the lemma and tell you what the inverse isomorphism is. So to prove that this forward map D goes to D bar is an isomorphism, what I'm going to do is I'm going to construct this two-sided inverse map, which is going to take a point derivation x in the tangent space, and it's going to send it to x tilde. And the definition of x tilde, well, it looks harmless enough, but I think I need to explain the notation a little bit. It's that composition. So m star here, this is the co-multiplication on the coordinate algebra, the comorphism of the group multiplication. So m star goes from k of g to k of g tensor k of g. And then there you can then apply the linear map identity tensor x. The identity takes the first k of g to k of g, and the x there, that's the point derivation we started with, so that takes k of g to the field. So that tensor product takes you from k of g tensor k of g to k of g tensor k, and the little bar there, that just means the obvious kind of contraction of that tensor product. So I mean, apply the canonical isomorphism from k of g tensor k to k of g, just kind of multiplying out that tensor. Okay, that's almost what I wanted. The inverse isomorphism is, I guess I need that word. So this inverse is not at all obvious at this point that x tilde is even a derivation, let alone a left invariant derivation. So that's actually the main effort we've got to do in proving this lemma. We've got to understand x tilde properly. So let's see if we can go ahead and do the proof. It's kind of just a calculation really, but so we need to understand x tilde. So x tilde is meant to be a left invariant derivation, so it's meant to take elements of the coordinate algebra and produce elements of the coordinate algebra. And to understand x tilde of f, since it's a function on G, I'd better understand how it acts on a group element. And so by definition of x tilde, that was that identity tensor bar x, m star of f. There's the definition. Okay, so I need to understand m star of f, the co-multiplication. Well, that's some tensor. So some linear combination of pure tensors. Let me maybe introduce some notation for m star of f. It's going to be some sum of f primes and f double primes. And then I can calculate this m star of f, and then I've got to do id tensor bar x on it, right? So I'm getting this sum. So I'm going to be doing x on the fi double prime, and I'm going to be leaving the fi prime. So it's that evaluated on G. Okay, so let's rewrite this a little bit more. So this is, remember, x is linear, so I can rewrite that as x applied to the sum I equals 1 to n, fi prime of G, that's scalar, and then fi double prime. Okay, so we're just processing the definition of x tilde. I need to compare this to lambda g inverse of f. So the left translation of f by g inverse. So what function is that? Let's think about what that does to an element h of the group. By definition of left translation, that's f of gh, which is m star of f on the pair g comma h, right? Because that's a multiplication. You can just bring it out the front and co-multiply the f. So m star f, that's the f prime, f double prime. So that's the sum I is 1 to n fi prime of g, fi double prime of h. And this was for all h. So actually, lambda g inverse f, it's just equal to that expression, which is exactly the expression we're seeing inside there. So I can do one more simplification to my x tilde formula. This is the same as x of lambda g inverse f. So I'm going to use that formula a bunch. So let's maybe name this fact dagger. Okay, so we're going to use this. I'm going to check that x tilde is a left invariant derivation, so that this is at least a well-defined function in the opposite direction. So there's two things to check. I've got to check left invariant and I've got to check derivation. So what have I got to check? Let me see. So for left invariant, I've got to check that if I do x tilde to some left translation of something, it's the same as doing x tilde to that function and then left translating the new function. So I've got to check that those two functions on our group are equal, and to check that they're equal, I'll just evaluate on some other element h of the group. So I have to check this identity. So that's the check for left invariance. I've got to summon up the courage to do it. Maybe let's write down what's the other check. What's the check for derivation that we've got to do? I've got to check that if I apply x tilde to a product, it's equal to applying, so this is the Leibniz, x tilde f1, f2, plus f1 x tilde of f2. So that's the second thing I've got to prove for derivation. And again, to check this, I'm just going to evaluate both sides on some element of the group. And so the right-hand side, when you evaluate on the group, because it's pointwise multiplication, that's evaluating each of these guys on some element of the group. Okay, so now I've really got to go ahead and do this, haven't I? So I can't really avoid this any longer. So we're just going to make this mindless calculation a little bit. So let's first of all check the left invariant. So let's start maybe here with the right-hand side. The right-hand side of this identity to be checked. It's x tilde of f. So this is definition of left translation. So this is g inverse h. But that's just, so now I'm going to use dagger, because that tells me how to calculate x tilde of f on some group element. It's x of left translation by the inverse of that element on f. But that's just because lambda was a group action, that's g inverse h inverse is h inverse g. And that's just, let me see if I've got this right, h inverse g, so this is x of lambda h inverse, so this is dagger again. So this is x tilde of lambda g f evaluated on h, and that is the left-hand side. We're done. Okay, so kind of just a sort of rather mindless check from all of the definitions, but the definitions are reasonably involved at this point. Okay, so that's the left invariance. Let's check the derivation property. So let's just start from the left-hand side. So again, I'm going to use dagger to evaluate this x tilde. So it's just x of the left translation of our function, which is f1, f2. But that left translation is an action by algebra automorphism, so it's lambda g inverse f1 times lambda g inverse f2. And now I can use that x is a point derivation, so it's x of that first function, and then it's the second function evaluated at the point, or it's the first function evaluated at the point x of the second function. And that's just, so now I'm using a dagger again, that's x tilde of f1 evaluated at g. And this stuff here, by definition of left translation, that's just the same thing as f2 of g. And this is f1 of g, x tilde of f2 of g. I guess I better put some extra brackets. And that is exactly the right-hand side. Okay, good. So our x tilde is now well defined. We have a linear map in the other direction, and all that's left to prove the lemma is that these two maps are indeed two-sided inverses. So if I start with a left invariant derivation, I bar it and then tilde it, it gives me back where I started. Or if I start with a point derivation and I tilde it and bar it, it gets me back where I started. So again, there's two different identities to check here. So for the first one, I need to check, so both of them I just need to check that they're equal on some function in the coordinate algebra of G. Why is that a G? I don't know. So those are the two identities I have to check. So for the first one, d bar tilde, I've got to check that these are equal as functions on G, so why don't I evaluate them both on an element of the group? And then the left-hand side, it's so now I'm using dagger, because there's a tilde here. This is d bar of left translation of f. But by definition of d bar, that's evaluation at E, d of lambda g inverse f. So that's just, let me see, what am I going to do now? I'm going to use that d is left invariant, so I can pull that lambda g inverse past the d, and then my evaluation at E, there it is. But this is just d of f on G by definition of left translation, and that's the right-hand side. Okay, and then the very last identity to check, we've got to check that x tilde bar of f is x of f, but x tilde bar of f, that's just x tilde of f evaluated at E. And now I just have to use dagger one more time. My x tilde formula, that's just x of lambda E inverse of f. But lambda's a group action, so translating by the identity doesn't do anything, so that's just x of f, which is the right-hand side. So all of those calculations, that's the end of the proof. So now we've identified this Lie algebra of left invariant derivations with the tangent space, these point derivations, via these two maps. Using this, we can transport the Lie algebra structure to make this tangent space into a Lie algebra too. So let's write the final formula. The commutator of two elements x and y of the tangent space of two point derivations is going to be, well, we're just lifting them up to left invariant derivations by applying this tilde map. Then we're taking their commutator as linear maps, and then we're composing with evaluation at E. So right there, that's the final definition of the Lie bracket on the tangent space. Let me do one example. So of course I'm going to do the general linear Lie algebra because that's the most important example of all. So for that we know that the tangent space, well, we've identified the tangent space with the same, with the vector space of n by n matrices. And we did that rather explicitly. For the vector space of n by n matrices, we had the basis of matrix unit. So Eij was the ij matrix unit. And as a point derivation, that was just a partial differentiation with respect to the ij coordinate function, and then composed with evaluation at E. So that's stuff we've discussed before. So the question now is to work out what's the Lie bracket on the tangent space. Well, you kind of know already what you're expecting, right? We're expecting that it's going to be the general linear Lie algebra. So in other words, the associative algebra of n by n matrices viewed as a Lie algebra via the Lie bracket. That's our GLN of K. Of course, we're expecting that the Lie algebra associated to the group GLN is the Lie algebra GLN. So we kind of know what the answer is already, right? So that tells us what we're expecting. Tells us that we're expecting the commutator of two basis elements of two matrix units. Well, so that's the matrix Eij times the matrix EKL minus the matrix EKL times the matrix Eij. And just by the way that matrix units multiply, that means it's the Kronecker delta jk EIL minus the Kronecker delta Li EKJ. So that's what we're going to prove. So we're going to show, in order to establish that, in order to prove that the Lie algebra of the general linear group is the general linear Lie algebra in all our coordinates, what we have to do is I basically have to prove this identity, but it's much easier to apply the map tilde and go to left invariant derivations. And so actually what I'm going to do is I'm going to show the corresponding left invariant derivations where the Lie bracket is the natural commutator of linear maps. Satisfies this identity. Okay, so that's my goal. That's what I'm going to prove. And okay, so to do this, what we need to do is we need to know actually what's Eij tilde. So this is a derivation from K of G to K of G. To understand a derivation, we just need to understand what it does to algebra generators. So let's see if we can calculate Eij tilde on the polynomial generator TRS there. So by lemma 1, that's this point derivation evaluated on the co-multiplication of TRS. And the co-multiplication of TRS is the sum. I'm running out of letters here. Let's maybe go to the letter U. TRU tensor TUS. And so that's, so I'm summing u equals 1 to n, so I've got to evaluate the identity on TRU, and I've got to evaluate EIJ on TUS, that's a scalar. But EIJ, it's just partial d by dt ij, followed by evaluation at the identity. So this gives me 0 unless I equals u and j equals s. So actually my sum collapses, u is just equal to I, and this is 1 providing j is s, so I'm just getting a Kronecker delta js there. So that's going to be, we're going to need that. So eij tilde on TRS, what you do is you look at the last two coordinates, you get the Kronecker delta, and then it's t of the first coordinates. Okay, so now I'm trying to show this so that we're getting the expected Lie bracket that's just matrix commutator. So these are left invariant derivations. To check that they're equal, it's just enough to check that they're equal on a given TRS. So that's what I'm going to do. Let's see what's the right-hand side. So that's delta jk EIL tilde of TRS minus delta Li EKJ tilde of TRS. And I've just calculated how to do these E tildes to the T's. You get another Kronecker delta for the second coordinate, and you get T for the first coordinates. And similarly, the second one, we get another Kronecker delta for the second coordinates, and we get T of the first coordinates. So that's the right-hand side. What's the left-hand side of the identity that we're trying to prove? So this is going to be EIJ tilde of, okay, so I've got to do EKL tilde to TRS, and then it's the commutator, so it's then the other way around. So that's EIJ tilde. So EKL tilde TRS, that's Kronecker delta, delta LS, TRK. And then I'm going to get EKL tilde Kronecker delta, the second coordinates, T of the first coordinates. Okay, it's rather a nightmare, but there we go. So what have I got? Kronecker delta TRS. So I now need to do the EIJ tilde on the TRK. So it's a delta JK, TRI. And this last term is this Kronecker delta LI, TRK. And I've got to compare. Did I really get the same thing? Delta, delta T, delta, delta T, yes. So it all worked. What I've shown is that the Lie algebra of the general linear group is the general linear Lie algebra, as we expected. Okay, so that's good. I'm going to do one more calculation today. We need to look at morphisms. So let phi from G to H be a morphism of algebraic groups. Then the differential d phi at the identity element, that gives us a linear map from the tangent space of G to the tangent space of H at the identity. This is a Lie algebra homomorphism. If you like, this means that there's a functor from the category of algebraic groups to the category of finite dimensional Lie algebras, taking an algebraic group to its tangent space at the identity viewed as a Lie algebra in the way we've just defined, and taking a morphism of algebraic groups to the differential at the identity. So to prove this, well, it's a little bit awkward, you see, because our definition of the Lie algebra structure was indirect. We really liked this space of left invariant derivations on G and left invariant derivations on H. So we were using these identifications. So the left-hand vertical map was what that was sending left invariant derivation D to evaluation at E composed with D. And the right-hand map was sending D, similarly, evaluation at E composed with D. I guess, let me be really careful. On the left, that's the identity element E of the group G. And on the right, that's the identity element E of the group H. So what I think what's convenient to do is to just kind of use this diagram. So let's let d phi from L of G to L of H be the unique linear map. So the diagram commutes. So that's really what I've got to do. I've got to understand this differential. How do I understand the differential upstairs at the level of these left invariant derivations? And once I've made this translation, I understand my d phi between L of G and L of H, then I'll be able to check quite directly that that's a Lie algebra homomorphism, because that's where the Lie algebra structure is kind of natural on these upstairs spaces L of G and L of H. So here's my claim. I claim that for D in L of G, d phi of D is the unique element of L of H. So the unique left invariant derivation such that, so here's the key property that tells you this d phi. D composed with the comorphism phi star is going to be equal to phi star composed with this d phi of D. So that's what we need to establish. This characterizes the image d phi of D uniquely. So let me try and check this quickly. It's not really too bad. Of course, d phi of D, so I'm taking a D in here. D phi of D is kind of uniquely determined by its image when I go east then south has got to be the same as its image when you go south then east. So it's determined by, so if I go, so let me go south then east first. So it's determined by d phi E of evaluation at the identity. This has to be equal to going east then south. So now I'm going this way. So this is going to be evaluation at H of d phi of D. Okay, so that equation uniquely determines this d phi of D. It's the unique element of L of H so that equation holds. Let me rewrite this just a tiny bit. So this is the differential, right? The differential is easy. The differential just composing on the other side with the comorphism. So I could have just written that as evaluation at EG and then d phi star. So this equation uniquely determines this left invariant derivation d phi of D. But I'm going to do one more kind of little slightly cunning thing. Evaluation at the identity of H is the same as the evaluating at the identity of G composed with phi star. That's dead easy to see. It's just the statement that phi sends the identity element of G to the identity element of H. So instead of putting evaluation at EG there, I can put at EH there, I can put evaluation at EG composed with phi star. Okay, so this equation certainly determines this d phi of d uniquely. And what I really just want to do is I want to just cancel those out, and that leaves me the equation that I'm after. It's not quite obvious that you have a right to do this, right? If this holds, I can certainly compose on the left by evaluation at EG, and I see that this holds. So the problem is how to get from here to the formula that I'm after. So what I'm going to do is I'm going to compose on the right. So what have we got here? These are all functions. This goes from k of h. You feed something in k of h in here. It's in k of g. It's in k of g. It's in k. Right, so these are both functions, both sides of this equation. They go from k of h to the field. So I'm going to compose on the right with, let me see, I think I'm going to compose on the right with lambda phi of g for g and g. So I'm starting from this equation. So I think I'm going to need to do this on a separate page. It's just a little fiddly, isn't it? So I've got this equation which definitely characterized our d phi of d, and I'm composing with lambda phi of h. Not phi of h, phi of g. For any g and g. And so what I'm going to use here is I'm going to use that phi star composed with this left translation by phi of g is just left translation by g composed with phi star. So this is pretty easy, and I'm just going to leave this as an exercise. Just plug in a function f in the coordinate algebra of h on both sides, and check that the results are equal as functions on g by evaluating on some other group element. So you just evaluate on an f and then on some other element of x there. So that's really straightforward to check. And so that means that you can pull this lambda past the phi star. It becomes a lambda of g. But d is a left invariant derivation, so you can pull the lambda g past. And, well, evaluation EG composed with lambda g, that's just the same thing as evaluation at g. That's really obvious. So when you do this, you can just pull this lambda to the right, and this becomes the equation lambda g composed with d composed with phi star. That's the left-hand side. And similarly on the right-hand side, this is a left invariant derivation by its definition. So you can pull the lambda past, and then you can pull the lambda past the phi star using this fact, and then you finally got this evaluation lambda g. So this is, I wrote lambda g. That was a mistake. That was meant to be evaluation at g. And similarly on this side, it becomes an evaluation at g, phi star, and then this d phi of d. This holds for all g and g, and so when it holds for all g and g, that implies that these are equal as functions from k of h to k of g. Once I've done that, this lets me, so I was trying to cancel off those, but to do it, you need to, you can cancel it off if this is evaluation at g for any element, and it's just at the identity. So you need to play this little trick. This proves the claim. Okay, so that was a little painful. So now we've got this nice characterization, this formula star. So now we understand this linear map d phi at the level of left invariant derivations. Now we can prove the lemma. So what am I trying to do? I'm trying to take two left invariant derivations d1 and d2 in L of g, and I'm trying to prove that if you apply this linear map d phi to it, I'm trying to prove that that's a Lie algebra homomorphism. So I'm trying to prove that it's the same as first applying d phi to d1 and to d2, and then taking the commutator of those linear maps in L of h. But the left-hand side is the unique element of L of h by my fact star, such that when you apply phi star to it, you get the same as just doing and I'm just checking that I'm getting this right, d1, d2 composed with phi star. So this is the fact star, the claim that we just proved. So we must check that the right-hand side has this property. Right, so to prove this equality, to show that the right-hand side is equal to the left-hand side, all I have to do is I've got to prove that the right-hand side is something which when you compose on the left with phi star, it's equal to the same thing. So I've got to prove that if I do phi star to the right-hand side, it's equal to d1, d2 composed with phi star. But now this is kind of easy. So what is it? It's phi star composed with, okay, I shouldn't have put brackets there. That was just the wrong notation to be using. So let's fix that up. This was composing on the left. That's what I wanted to write. There we go. This is the notation is kind of more complicated than we really want, isn't it? So I've got to check that phi star composed with d phi of d1 composed with d phi of d2 minus phi star composed with d phi of d2 composed with d phi of d1. But now I can use the property star. When I pull phi star past, it just cancels out the d phi. And then I pull the phi star past again, and so by that property star, this is indeed d1 composed with d2 composed with phi star minus d2 composed with d1 composed with phi star, and that's exactly that guy. And okay, that's kind of a nasty argument. That's kind of a tricky calculation there. Okay, I think I better stop because I've done an awful lot of calculating today. Now the theory of Lie algebras is actually in place, and next time I'll just be able to do lots of examples and you'll see how nice this is.